In our last class, we have discussed that first we have some subring, right? So, what is subring? Basically, we have discussed there are two criteria. If it is satisfying, so then your that set will be subring, right? That a subset of R. R is a ring. So this S is said to be subring if what happen, one is your A belongs to S, B belongs to S, this imply A minus B belongs to S, right? And second thing is your A into B belongs to S. These two property is your for subring. Next we have discussed ideal, right? So what is ideal? So ideal basically also a subring, but it needs one more property. Basically, for left ideal you need R dot A belongs to S. So I, we can say, is a ideal if first your I is a subring, right? And second thing is your that R into A belongs to your I, for all R belongs to R and A belongs to I. This is for your left ideal, right? Second is your A into R belongs to I, for all R belongs to R and A belongs to I. This is for your right ideal. Okay, so if both property satisfy, then we will say that ideal. And in this ideal, we discuss some of the example. This is done. After that, I think this is, we have discussed that if your S is a ideal and T is a ideal, then basically S union T is also a ideal. Maybe this may be your homework in your last class. Okay, so after that we start our online classes. Okay, so first we start with a theorem. This theorem already you know in group theory. Like suppose you have a G is a group. Okay, then suppose you have two subgroup H and K. H and K be to subgroup of G, then you know H union K is a subgroup of G if H subset of K or K subset of H, right? I think this thing discussed in your maybe SEM 3. So similar thing is here for ideal version. Okay, so let's discuss this. Okay, so theorem, let S and T be two ideals of a ring R, then S union T is an ideal of R if and only if either S subset of T or T subset of S. So this is if and only. Okay, so one sided is very easy, right? So for example, if S intersection T, then S union T will be what? This will be T, right? So is an ideal because T is an ideal, right? Ideal. And oppositely obviously same. If T is subset of S, then S union T will be S. is an ideal. So they are nothing to prove. Okay. Now conversely, so let S union T be an ideal. Okay, so if your S union T is an ideal, so what you have to prove basically, either basically if you think like this, so this if okay, if this is your S, so you have to prove this T is like this, right? Or if this is T, then your S will be like this. Okay, this type of scenario. Okay, so anyway, if this scenario we will prove with contradiction. Okay, so for example, if this scenario is not happen, so how this structure looks like. So obviously you expect there will be, this structure will be like that, right? If this is not happen, or this will be like something like this, right? So we'll assume this type of scenario. Okay, so let neither T subset of S or S subset of T, like this type of scenario. So in this type of scenario, you have T minus S. Okay, then T minus S and S minus T is non-empty, right? You know what is the set subtraction, right? Non-empty. So whenever you have this type of scenario, obviously let X belongs to T minus S and Y belongs to S minus T. Okay, so like T minus S, so T minus S will be like that. So suppose this is your X, I am erasing this picture. Okay, and Y is like this. Okay, okay, so if your X belongs to T minus S, so what it implies? So this is imply X belongs to T and X does not belongs to S, right? And Y belongs to S, this implies this type of thing, and Y does not belongs to T, right? This is clear from your picture, right? Okay, fine. But you can say your you have to think from S union T, right? S union T is an ideal. Remember this thing. So you see from here you can say S union T, where this is belongs. X belongs to S union T, right? Because X belongs to T, so it belongs S union T also, and Y belongs to S union T also, right? Now you just think in this way, that since your S union T is ideal, so you have X minus Y belongs to S union T, because obviously first it is an Subring property, it's hold, right? We have discussed all the property here also again. Anyway, so since S union T is an ideal, so if you have X minus Y belongs to S union T, okay, so what you can say from here. So whenever it is belongs to S union T, obviously is imply x minus y belongs to S or x minus y belongs to T. One of the scenario must happen, right? Now if x minus y belongs to S, now you see x minus y belongs to C and y belongs to S, right? Y belongs to S. So from there, if you add this to thing, so you can say x belongs to S, right? But what is this thing? It does not belong to S, so a contradiction. Similarly, if you have x minus y belongs to T and y belongs to x belongs to, I think, T, right? X belongs to T, right? So this imply x minus y, basically y belongs to what? T. This is contradiction to this scenario. Contradiction. So what you have? So hence our assumption is wrong. So S union T, so S subset of T or T subset of S, and like that. This is a important theorem. Okay, next we have one more theorem. Okay, remember S union T, this is union, S plus T, these two things is different. Already we have discussed in the class. This is basically just two set union. Okay, but S plus T is like S plus T time of element, where S from S and T from T. But here this element says like x such that x belongs to S or x belongs to T, right? This type of scenario. Okay, so here we have a theorem. Let S and T be two ideal of a ring R, then S plus T equal to S plus T. That is the definition, you know. Is an ideal of R and it is the smallest ideal of R containing both S and T. Okay. So first you have to prove S union T is an ideal, then you have to show that this is the smallest. Okay, so first we will show this is ideal. So you see, obviously S and T is an ideal, so 0 belongs to S, so from there you can say this S plus T is a non-empty. Okay, clearly S plus T is non-empty as 0 belongs to S plus T. Anyway, this is just easier one. Now first, before the ideal also you have to prove the Subring property, right? Subring means if you have two element from that set, their difference will be in that set. Okay, and remember this property, whenever you have to prove the ideal, this ideal, here in the Subring you have to prove this property where this AB belongs. A belongs to S, B belongs to S. So instead, whenever you have to prove the ideal, so you prove this property and this property. That is enough, right? Because here this R is from R, which is more than your S or I. right? So you have to prove the addition one, subtraction one, and then this ideal poverty, then it will be done. Okay, so let a belongs to s plus t. Okay, so how this a looks like, and take another element, b belongs to s plus t. So obviously a will looks like s1 plus t1, and b will be s2 plus t2. Now how a minus b looks like? S1 plus t1 minus s2 plus t2. So from there you have s1 minus s2 plus t1 minus t2. So from there you can say this thing, this is s, this is t, right? So you can say this is belongs to s plus t. This is done. Okay, now take r belongs to your main set r. So what you have to show? R into a belongs to that set, and a into r also similar way. So r into a if you do, so basically s1 plus t1, right? So r s1 plus r t1, and remember s is an ideal, so r s1 belongs to s, t is an ideal, so r t1 also belongs to t. So from there you can say s plus t, right? So here basically since s and t is an ideal, this is required. Okay, similar way you have a into r, so basically s1 plus t1 into r, so s1r plus t1r, this is belongs to s plus t, and you have to write the same line. Fine. So this proves thus you have S union T is an ideal. This is done. Next part. Now what you have to prove, that S plus T is the smallest one. Okay. Smallest means so basically this is your S, and suppose this is your T, and so basically this is itself this S plus T. This is not the union. Okay, this set may be larger. Okay, because this is the addition S plus T. Obviously there will be some other element. Okay, for example, if I say S is equal to 0 comma 1 and T is equal to 1 comma 2, so how your what is your S union T? So you will say this is like 0 comma 2 or minus 1 maybe, because 1 is not there. But if I say what is your S plus T, you will say like 0 anyway. So all the possible combination you have to take. So basically 0 1 for this one you have 1 comma 2, and 2 you have 3, maybe 1 to 3, this type of set you will get. Right, this is the difference between these two things. Anyway, so this S plus T will be the smallest one, that you have to prove. Okay, so here also we'll consider, suppose there are some ideal that contains S union T. Okay, so thereafter we will show that S plus T is actually containing this inside that P. Okay, so let P be an ideal containing S containing both S and T. Okay, so let P be in. Okay, this is fine. So this is S, this is T. Suppose this is S union T. This is just rough picture, we don't know what is the exact structure. Now you are considering that there are some P and there is some ideal which is containing S and T both. So this is like you are thinking there is some structure P. Now you have to show this S plus T, that the rectangular box, this is actually inside P. In this way you have to prove. Okay, so let X, so your job is your S plus T subset of P. This you have to prove, right? So let, obviously we will start from any element from this one, then we will show this is inside P. That's it. Let X be any element from S plus T. So obviously X will be looks like some S1 plus T1 like earlier. For some S1 belongs to S and T1 belongs to T. Fine. Okay, now see, P is actually contain S and T both. So obviously S subset of P and T is also subset of P. So from there you can say S1 belongs to P and T1 is also belongs to P, and since P is an ideal, right, this is an ideal, so you have S1 plus T1 belongs to P, right? So this proof X belongs to P. So this proof, what this proves, S plus T subset of P. So you have considered any ideal P that contains S and T. So this proves that S plus T is the smallest. Okay, this proves that okay, fine. Now just think, what is the property of ideal? Ideal, basically this is a subring that is okay. Then you have R dot A or A dot R. This type of thing belongs to your that ideal set, right? This R belongs to what? This R is from the main ring R, right? Now you just think, if your ideal contain your unity, that is your one unity, like whatever its unity, so if it contains it unity, so obviously this is will be your R, right? So then actually I will be R, right? So that's why you have the next theorem. If an ideal S of a ring R with unity contains a unit of R, then S equal to R. Okay, so this unit sense is actually if your element is unit, like A is unit, so A dot A inverse, that means your one belongs to that set, right? So in this way it is in the ring you have unity and contains a unit of R. Okay, so how to prove? So let These are very easy proof. If it is in class, obviously I don't do. This is your homework anyway. So let R be a ring with unity 1, and let S that U be a unit in S. Okay, so U unit, so obviously there exists U inverse belongs to contains a unit, and let so U is a unit, so obviously there exists U inverse. So we don't assume that this will be belongs to S, so but obviously this is unit, so U inverse exists. Okay, so U inverse belongs to this. Okay, so since such that U into U inverse equal to U inverse into U, this is your 1. Okay, now 1 belongs to this set, right? But since your S is an ideal, so obviously this 1 belongs to your S, right? Because you just think R into A types. Here A is looks like your A is looks like your this U element, R is looks like your U inverse. So from there you can say this 1 belongs to S, right? So if your 1 belongs to your that S, that's it, nothing you want, you require, because now let A belongs to R, right? So since S is an ideal, so obviously then you have A into R type. If I into no R into A, yeah, so basically R into A, 1 dot A belongs to S, right? So that means what it's imply, A belongs to S, that means what imply that R subset of S, right? Now you know that S is actually subset of R. Again you are saying R is also subset of S, so what it proves, since S is an ideal, so ideal of R, so A subset of R. So combining these two, what you have, hence you have S equal to 1. Okay, so remember that if 1 belongs to that ideal, that's it, nothing you have. Okay, this is done. So similar way you just have a look on this theorem. This is your homework 1, just have a read. A division ring has no non-trivial proper ideal. What is the do you mean by the non-trivial proper ideal? Basically you know that 0, that singleton your 0 set, and the whole R, these are itself a ideal, right? So that type of thing we don't want. So we are interested this not proper, that means there will be some I that is strictly subset of R and that containing 0, like that in the middle portion. Okay, so if you have some division ring, so then basically there are no proper ideal, non-trivial obviously, that 0 except your 0 and R. How you have to prove this type of thing? Basically you know division ring, every element is your unit. All right, so if you have that unit type of thing, and already we have proof that if you have that unit, so one belongs to that set, and if your one belongs to that set, so that will be equal to your the whole one, right? So in this way you have to prove. So this is your homework, just write up, nothing else. Okay, now obviously you know your field is actually division ring, right? So you can say in a field has also no non-trivial proper set, right? You know, in the division ring, if you add the commutative property, that becomes the field, right? So a field also have no non-trivial proper ideal. So this is your coronary or remark that a field has no non-trivial proper ideal. Okay, this is the thing. Okay, next there is a definition. This type of a ring where you have no non-trivial proper ideal, this type of thing is called actually simple ring. So write the definition: simple ring. A ring is said to be a simple ring if it has no non-trivial proper ideal, like field, right? That field is a simple ring. So you know, field example all that Q R, this type of thing. Okay, but remember, in the field commutative is required, but it may happen your simple ring is not commutative, so that it is not imply that every simple ring is your field. Okay, anyway, okay, now we have the next one. Next theorem: a commutative ring with unity having no non-trivial proper ideals is a field. So you have a commutative ring with unity having no non-trivial proper ideal is a field. Okay, so what you have to prove the field. So what you have to prove, basically, you know the definition of field, that every non-zero element is your unit, right? So this thing you have to prove. Okay, so let we will consider some element. Our job will be, there will be some inverse of that, right? You have to show basically this is unit, that's it. Okay, so let R be a commutative ring with unity 1 and the only ideals of R is your 0 and R, right? So because they are no non-trivial, so there is a 0 and R, that's it. Okay, now you are considering any arbitrary non-zero element. Let A be a non-zero element of R. Okay, so now consider R into A. What is R into A? Basically R into A type, where R belongs to R, this type of set. Okay, fine. Now our job will be will trying to show that this is actually a ideal, but obviously it is no, it does not have any proper ideal, so obviously this should be the whole R. So then there is some array that will be your 1, right? So in this way we will try to prove. Okay, so first your job is you have to prove this is a ideal. Okay, how to prove? So let U and V belongs to RA. So this, and then what you have, then U equal to R1 into A and V equal to R2 into A, right? For some R1 R2 belongs to R. Okay, this is you have. Now obviously U minus B, this is very easy, that you can able to prove this is this type of thing. So obviously this is there, right? Fine. Now for any R belongs to R, if you do R into U, so what you have, R into R1 into A, just using ring property. So you have this type of thing belongs to R into A. So this proof that your R is a left ideal, right? Basically these two things you have to prove for the ideal. So hence RA is a left ideal, and you know this is commutative. R is commutative. So if your this is commutative, so you can have A into R is also commutative. This is also a ideal. So combining these two, so you have R into A is an ideal. So if you prove R is equal to ideal, and you know it has no proper subset, so what you have, obviously you see RA cannot be 0, right? So what you have, only R equal to R. Since R has no proper ideal, so RA will be your R. So since 1 belongs to R, you know it is written at the first line. So obviously there exists some B belongs to R such that your B dot A will be 1. This proves A is unit. So you have taken some random element, right? So every non-zero element of R is unit. So this proof R is a field. Hey, Anikda. Okay, I am stopping the class here. We will discuss in the next class. Okay, bye.